Hello students, welcome to this final video session of the geometrical evaluation of Z transform. Okay, so we assume that a transfer function will be given to you and we try to evaluate the frequency response or h of Z at any given point, okay, provided that point is lies in the region of convergence. Okay, so this is nothing but a theory on complex numbers actually, because all the functions of Z in general are complex numbers, and we know that complex numbers extend the real numbers. Real numbers are subset of complex numbers with the imaginary part being equal to 0. Okay, so and this helps you in the design of the filters, okay, various filters, low pass, high pass, and band pass, band stop, so on and so forth. Okay, so here the theory is, so there are two ways to characterize an LTI system, right, and both are equivalent because so I have an input in the time domain, so the output is y of n. So if I take the Z transform of all the quantities here, right, so x of Z, this becomes my h of Z, right, and this becomes my y of Z, and I can get back y of n, x of n from these functions, h of n from these corresponding Z transforms by taking the inverse Z transform. Okay, so the relation between the time domain quantities, as you know, is given by the convolution sum. Okay, so my y of Z, right, so this is your modulation theorem. So from the second equation, I'll take the Z transform of the first equation, so I get second. Okay, and I manipulate it so that okay, so where h of z is called as the transfer function. Okay, fine. So moving ahead from here, right, so I can either represent the given LTI system, linear time invariant system, using the impulse response or using the transfer function. Okay, so if I take the inverse transform of the transfer function, I get impulse response. If I take Z transform of the impulse response, I get the transfer function. Okay, so now moving ahead from this, so I'll take two examples and I'll tell you how to geometrically evaluate. Okay, so one of this is okay, so this is your first order FIR. FIR stands for finite impulse response. Okay, I'll tell you why it's finite impulse response. Low pass filter. Okay, fine. Okay, so if you take the inverse transform of this, what you get is, so my h of n will be equal to half, okay, plus half of right. So you see that, so if you plot this impulse response as a function of n, what you get is, right, so this is what you get. So this is h of n and the axis is n, so that you can see that the length of this impulse response is finite. Okay, it has two impulses one at n equal to 0, and one is the shifted impulse present at n equal to 1, and both scaled by half, by a factor of half. Okay. So moving ahead from here, okay, so how to evaluate the frequency response? So and one important point of this FIR filters is that the Dtft always exists, because the summation will always be something finite. Okay, so you sum half, you take the sum of this impulse response, right, and substitute in that condition, so you'll get the sum will be something finite. Hence h of z will, the term that we use is, it will be always stable, and hence the Dtft exists. Okay, I'm sorry. Okay, fine. Now to evaluate the Dtft, so Dtft evaluation is important because so these filters are widely used in various applications, right? For example, as you know, the MP3 format, the audio that is stored on your phone, right, is in the MP3 format, so which is a digital format, and before it is stored, so it passes through various steps. Okay, and suppose, say, if you want to increase the bass present in the audio, right, what we do is we basically enhance the low frequency contents, right? So the bass corresponds to the low frequency contents. So there what we do is we basically allow low frequencies to pass, and we attenuate the higher frequencies, so that you get the higher bass content in the final audio file. Okay, so this is one of the filters that is used, or a different order filter might be used depending on the type. So this is the idea, right? So we basically use, this is the simplest filter. Okay, so these filters are used in practical applications. Okay, and to evaluate I'm sorry, so to evaluate, what I'll do is, so suppose if I want to find out the frequency response of this filter, low pass filter, at z equal to, let's say, at omega equal to pi by 2 radians. Okay, the unit of this is radians. So how to evaluate that? So draw the z plane. Okay, so draw the unit circle. Okay, draw the unit circle. Right. So once you draw the unit circle, so you note down you mark the zeros and poles. So zeros are marked by circles. Okay, and here for this function, 0 is present at z inverse equal to -1. Okay, at omega equal to pi, right? So here, and for transfer functions that we are interested in, so there will be equal number of poles and zeros. Zeros are the values of z at which h of z is equal to 0, and poles are the values at which h of z goes to infinity. Okay, and for this the pole is present at z equal to 0, right? Substitute z equal to 0, you can see that the value of h of z goes to infinity, right? And for the transfer functions that we will usually look at, right, so we have equal number of poles and zeros. We have one pole and one zero for this system. Okay, and suppose if I want to evaluate the value of the frequency response at omega equal to pi by 2, what I'll do is I'll mark this point. Okay, so this is nothing but the complex number theory, right? So I'll substitute z equal to e power j omega pi by 2. Okay, so I'll tell you how this theory comes. So this is the vector from a 0 to that point, right? And this is a vector from pole to that point. Okay, now so this is nothing but the z plane, right? So this theory is nothing but, so h of z is half 1 plus z inverse. Okay, and this plot where you mark poles and zeros is called as a pole zero plot. Okay, so if you simplify this, you will get okay. Write this, I'll write it as z minus 0. Okay, so fine, into half, of course. Okay, now so suppose if you want to find the value at h of z equal to, let's say at z equal to 3, right? So if you notice, so this will be half of 1 minus of minus 3, okay, divided by, or so I'll write it in another format, it doesn't matter, right? So the geometrical interpretation is very important here. So 3 minus of minus 1, okay, divided by 3 minus 0. Okay, now if you want to calculate the length, right, so that is given by the mod value of this at z equal to 3, right? So in equation you will substitute z equal to 3 and it will be 3 plus 1 divided by 3, so it will be 4 by 3 into half, which is 4 by 6. Okay, you can see that the same value will appear by this interpretation, right? So you will take the length of the numerator as well as the length of the denominator and divide it up. Okay, so you can see that the numerator part is nothing but the vector that is drawn from the 0, right? So the initial point is here, the initial point is given by the second quantity. Okay, so how do you draw a vector? If you have a vector from point A to point B, right, so you'll say that this is a vector b minus a. Okay, so where b is the final point, a is the initial point. The same thing goes here, right? So minus 1 is the initial point and 3 is the final point. Okay, so you draw a vector starting from minus 1 and that goes up to 3 and measure its length. Okay, so this will be, since it's a simple example, so you'll get the length equal to 4, right? And the same thing goes here for the denominator quantity, right? So actually I have drawn it to e power this omega equal to pi by 2. So you can extend this theory to this z equal to 3, right? Okay, now the denominator will be equal to 3 minus 0, which is 3. So the length is 3 and half. Okay, so you'll get the length, the value of the function at z equal to 3 to be equal to 4 by 6. Right, the same thing, same theory can be extended to this, where z equal to e power j omega, right, 1 into e power j omega, because the point is lying on a unit circle. So unit circle implies r equal to 1 and this point is specifically omega equal to pi by 2, which is equal to j. Okay, z equal to j, so the numerator will become j plus 1 divided by j minus 0. Okay, and substitute the value and you will find out that the value will be equal to how much? What is the value of 1? Okay, so we'll evaluate it geometrically here. So this is nothing but half e power j pi by 2 minus of minus 1, okay, divided by e power j pi by 2 minus 0. Okay, so this is half into, what is e power j pi by 2? It is nothing but plus j. Okay, so j plus 1 divided by j. Okay, so this will be nothing but half of 1 minus j. Okay, right. So if you want the modulus or the magnitude response as it is called, for the frequency content whose value is pi by 2, right? So we get half, okay, into what is the how do we calculate the magnitude of 1 minus j? It is square root of 1 square plus square root of minus 1 square, right? So which is equal to square root 2, okay, and there is a half that is present here, okay, so this will be equal to 1 by root 2, right? Fine. So if you notice, so the length of this vector is always 1 because it is the vector starting from origin to the point on a unit circle, hence this is nothing but a radius which is equal to 1, and this length will be equal to 1 by root 2, okay. So 1 by root 2 by 1 will give you the value of the magnitude, right? So this is how you evaluate the geometric, how you evaluate the Z transform geometrically, right? And this is the response of the filter for the frequency content whose value is omega equal to pi by 2, okay. So if you pass a frequency, right, so this is what you do for an amplifier, but you will pass analog signals. So if you pass a digital signal whose value is cos pi by 2 n, okay, so what you get at the output of this is, so I am talking about the magnitude, so the magnitude will become 1 by root 2 cos omega, so the frequency will remain the same, pi by 2 n. So this is the meaning, right? So similarly, if you pass cos pi by 4 n, so the magnitude that you multiply will be different. So suppose if you pass a cos pi by 2 n, so the magnitude will become a by root 2 cos pi by 2 n, okay. So that's about the geometric evaluation. So thank you, students. So if you have any doubts, you can always mail me, right? So regarding any of these sessions, so I have tried my best to cover almost so what I felt was important, right? So we'll stop here. Thank you very much for attending. Okay, thank you.